Director Holden, Secretary Moniz, Director Damer, awardees, distinguished guests, ladies and gentlemen, good afternoon. It's my pleasure to welcome you to the United States Department of Energy for this wonderful occasion, to honor two distinguished scientists in front of you with the 2014 Enrico Fermi Award. It's wonderful to have so many of you here to share this occasion with the laureates. I'm Lynn Orr. I'm the Undersecretary for Science and Energy, and I have the privilege of overseeing and directing the programs at the Department of Energy that are driving transformative science and technology solutions through coordinated planning and management across the Department's science and energy programs. So these awardees clearly demonstrate the depth and breadth of this mission, and we're proud to support and honor them. The Fermi Award is a presidential award and is one of the oldest and most prestigious science and technology honors bestowed by the U.S. government. The Enrico Fermi Award is given to encourage excellence in research and energy science and technology benefiting mankind, to recognize scientists and engineers and policymakers who have given unstintingly over their careers to advance energy science and technology, and to inspire people of all ages through the examples of Enrico Fermi and the Fermi Award laureates who followed in his footsteps to explore new scientific and technological horizons. The awardees receive a citation signed by the President of the United States and the Secretary of Energy, a gold-plated medal bearing the likeness of Enrico Fermi, and an honorarium. The Fermi Award is administered on behalf of the White House by the Department of Energy's Office of Science. Recipients have included people like John von Neumann, Ernest O. Lawrence, Eugene Wigner, Glenn Seaborg, Hans Bethe, Edward Teller, and J. Robert Oppenheimer. So it's a good group. In this tradition, the Enrico Fermi Award continues to recognize scientists of international stature for their exceptional scientific, technical, engineering, policy, and/or management achievements related to the broad missions of the U.S. Department of Energy and its programs, and this year is no exception. We continue this proud tradition as we present the Enrico Fermi Award to two recipients. First to Dr. Claudio Pellegrini, Distinguished Professor of Physics Emeritus in the Department of Physics and Astronomy at UCLA, and also now with SLAC National Accelerator Laboratory. And also to Charles V., better known as Chuck Shank, a senior fellow at Howard Hughes Medical Institute and laboratory director emeritus at Lawrence Berkeley National Lab. So I extend my personal congratulations to the two of you, the recipients of the 2014 Enrico Fermi Award. The department thanks you for your many contributions over the years, and we're not letting you off the hook. We look forward to your continued excellent work in the years ahead. And now it's my pleasure to introduce John Holdren. John Holdren has served as the Assistant to the President for Science and Technology and Director of the White House Office of Science and Technology Policy for closing in on 7 years now. I don't know if that's a record, but I'd be willing to bet it's right on, it pretty much has to be close to that. So John, you're on.
Well, thank you very much, Lynn. It's really a pleasure to be here today representing President Obama and the whole White House Science and Technology team to take part in this public recognition of the achievements of two really exceptional scientists, Dr. Claudio Pellegrini and Dr. Chuck Shank, and to congratulate them on their receipt of the Fermi Award. Drs. Pellegrini and Shank and their spouses met earlier today with President Obama at the White House to receive his personal congratulations and thanks. And it was great fun. I'll say more about that in a minute. The Fermi Awards, as has already been noted by Lynn Orr, recognize some of the most distinguished and accomplished scientists in America. He listed a number of the past awardees, overlap with my list, but in addition, I will mention Dick Garwin and Leon Lederman, two of my other favorite former winners of the Fermi Award. This year, the award recognizes work that has dramatically expanded our ability to explore and understand the frontiers of matter and energy. I'm not going to steal Secretary Moniz's thunder by describing the scope and significance of those accomplishments in detail, but I will just say that not many scientists can claim to have opened up a whole new field of scientific endeavor in the way that Drs. Pellegrini and Shank have done, resulting in both rich new insights and important applications to real-world problems. Recognizing scientific accomplishments that are highly creative and that also have a major impact on science and society as a whole is actually one of the more uplifting parts of President Obama's job and of mine. The president came into office in 2009 promising to restore science to its rightful place in American government, and he has delivered on that promise in a number of ways. During his time in office, he's appointed to high-level positions in his administration 5 Nobel laureates in science, another 25-plus members of the National Academies of Science, Engineering, and Medicine, the first ever chief technology officer, the first ever chief information officer, the first ever chief data scientist for the U.S. government. And of course, to really understand the scope of his commitment, you only have to ponder the caliber of the scientific and engineering leadership that he has provided for the Department of Energy, well represented up here. President Obama has also used the bully pulpit of his office to talk more about science, technology, and innovation than any previous president, maybe more than all previous presidents combined. Gave it prominent mentions in both inaugural addresses, every State of the Union address, 2 addresses to annual meetings of the National Academy of Science, major speeches, many major speeches on space policy, advanced manufacturing, clean energy, climate change, STEM education, and a lot more. He's launched more major initiatives in science, technology, and innovation than any previous president. Initiatives on clean energy and energy efficiency, on climate change, on neuroscience, on precision medicine, on strategic computing, broadband, information technology for more participatory and efficient government, STEM education and inclusion, and again, many more. And he's hosted an unprecedented array of White House events highlighting science, technology, and innovation. That includes 5 White House science fairs, a maker fair, and 2 White House astronomy nights for kids on the South Lawn, the most recent of which took place just last evening, with some 300 middle school kids, teachers, parents, looking through telescopes, examining moon rocks and meteorites, and mingling with administration science and technology leaders, media science personalities, and no fewer than a dozen former and current astronauts. I think that's the most former and current astronauts assembled in one place in the White House in history. As with today's Fermi Award winners, the president has made a practice of personally greeting in the White House the American recipients of the most distinguished prizes in science, engineering, and medicine, including the Nobels, the Kavli Prizes, the National Medals of Science, and the National Medals of Technology and Innovation. He also routinely greets personally the finalists in the Intel Science Talent Search, the winners of student math competitions, and the winners of presidential awards for STEM teaching, STEM mentoring, and early career achievements in science and engineering. For the president, these moments provide the uppers that help offset the many downers that go with his job in today's world. And I can tell you that his meeting in the Oval Office this morning with Dr. Shank and Dr. Pellegrini and their spouses, Heather and Maria, was no exception. It was another one of those uppers. And I can tell you that given the other issues the president is dealing with this week, it was most welcome. Let me then just conclude by saying how pleased we are in the federal science and technology community with this year's Fermi Award going to Claudio and Chuck, and let me thank them again on behalf of the President for providing today's science and technology upper. Lynn?
So my next task is to introduce someone who truly needs no introduction for this audience. That's Secretary of Energy Ernest Moniz. He's worked for decades on energy matters at MIT, at OSTP, at DOE, and his prior appointment as the sole, he reminds me now and then, the sole Undersecretary for Science, Undersecretary of Energy in the Clinton administration. He's just completely clearly the most well-qualified energy secretary we've ever had, so it's a pleasure to ask him to say a few words. Ernie?
Well, thank you, Lynn. This suggests he's going to be coming tomorrow to my office with a request. But John said how much the president enjoys these scientists, scientists, science awards, etc. And I have to say that for me as well, there are very few pleasures that are greater than opportunities like this one to have the opportunity to recognize people of the caliber and the accomplishment of Claudio Pellegrini and Chuck Shank. I do want to also welcome their family and friends here today, as well as Italian Ambassador Bisogniero. I don't know if this is a coincidence that you came today, but it's always a pleasure to welcome you here. Also, I'd like to recognize our Deputy Secretary, Liz Sherwood-Randall. As John said, these are really very prestigious awards, the Fermi Awards, certainly among the oldest and most prestigious, given by the government for lifetime achievements. Again, in various aspects of the use, control, production of energy and matter. As you know, its namesake, Enrico Fermi, obviously a legendary physicist, achieved the first nuclear chain reaction, as we all know, on the squash court under Stagg Field at the University of Chicago, and the apparatus, as Fermi described it, was, quotes, a crude pile of black bricks and wooden timbers. Now, I think if one sees today the outcome of the work of Claudio and Chuck, you get a different impression in terms of some rather impressive equipment, but I'll come back to their specific activities. A decade after Fermi's work, President Eisenhower on the Atomic Energy Commission honored Fermi with a special award, and regrettably he died only a few days later, but that really is the genesis now of the Fermi Award, and certainly he really lives on with this award that recognizes the highest level of scientific accomplishment, aligned with the department's responsibilities in terms of, again, probing, utilizing energy and matter. The past recipients, I won't go into again the names, since we've had quite a few mentioned, but you have them in your booklet, and again they are obviously an honor roll of American scientific achievement. I like to say that the Department of Energy is at its core a science and technology organization. Sometimes the diversity of missions looks confusing, but the thread is science and technology, and I believe that the department and its laboratories, the universities we work with, the industries we work with, are clearly a critical part of this country's very powerful scientific enterprise. And it's, again, people like Claudio and Chuck that really are at the foundation of that powerhouse of innovation that really drives this country's economy, security, environmental stewardship, and other critical activities. So let me say a few words about each of the awardees, starting with Claudio Pellegrini. I might add that John mentioned the very engaging event this morning with the president. The president's again, appreciation for science, as John said, is tremendous. It's clearly the only reason that John has hung in for 7 years, is that the president keeps challenging him on that. But I want to add something that John didn't say. The long discussion about Hawaii. Chuck has now been living in Hawaii for I forget, it was 12 years. I think it was. I think you said something like that. And he and his wife had lots of exchanges with the president in terms of very familiar to them schools and other things that were apparently large, great landmarks. But it was really fun. But Claudio emigrated from his native Italy in 1978 to become a senior physicist at Brookhaven National Lab. And then a decade later, going to UCLA, where he is now a distinguished professor of physics emeritus. He's receiving the Fermi Award for, and I quote, pioneering research advancing understanding of relativistic electron beams and free electron lasers, and for transformative discoveries profoundly impacting the successful development of the first hard X-ray free electron laser, heralding a new era for science. And of course, accelerators writ broadly are clearly one of the core competencies of this department and one of the critical tools and one of the great contributions made by this department and pioneers like Claudio to what is now a critical technology that just permeates so many activities in our society. These free electron lasers that Claudio in particular has developed make them highly desirable in disciplines from chemistry, the structural determination of molecules in biology, medical diagnoses, non-destructive testing, and we could go on. There's certainly some specific uses can include laser surgery, targeting fatty plaques in arteries. We all know what that does. And also in the national security realm, directed energy weapons. But I can tell you he's done even more than that. As a visiting researcher and scholar at several of DOE's national laboratories, numerous universities here and abroad, and even more panels and committees in every setting, he freely shares his insights and his leadership, enabling countless other researchers to advance their work in a broad range of fields. And I just want to say that one of the reasons that I certainly really appreciate today's awards to both Claudio and Chuck is the fact that not only are they outstanding scientists, not only did they do incredible science, but their work has created tools that have enabled so many other scientists to do first-rate work, and I think that's a common characteristic in both of their activities. So, turning to Chuck, our other awardee. He earned his PhD in electrical engineering at Berkeley and began a career at Bell Labs. But he then returned to Berkeley as director of DOE's Lawrence Berkeley National Laboratory and really initiated a really terrific array of science research initiatives, including with the light source at Berkeley. His award citation reads, quote, for the seminal development of ultrafast lasers and their applications in many areas of scientific research, for visionary leadership of national scientific and engineering research communities, and for exemplary service supporting the National Laboratory Complex. His pioneering discoveries and inventions enabled ultra-fast lasers and measurement techniques that have opened up what have been an inaccessible world previously of ultra-fast dynamics. Largely with his work, the term femtoseconds entered common parlance, at least among scientists and engineers, and as they, again, similarly to with Claudio, as they research in very diverse areas of energy science, material science, physics, chemistry, biology, and perhaps his greatest mark, even beyond that, has been on scientific leadership. Again, he's worked with DOE scientists, other national labs, putting together new initiatives, working in things like getting going the Human Genome Project and the Nanotechnology Initiative. So he's been an enormous contributor through his science and through his leadership in the science community. And again, thank you. I thank both Claudio and Chuck for their tremendous contributions and their well-deserved Fermi Awards. So again, no question. These are again two awardees, excuse me, very much in the at home in that list of luminaries that we heard earlier. Again, they've opened up new realms. They've enabled others to do fabulous science. They have been inspirations, I think, to many of us, and we thank you both for earning the Fermi Awards. Thank you.
So these two guys have worked together a lot. So now they get to work together on one more thing, at least, and something that's fun. They're the pair who will bestow the medal and the certificates. So if you two could take your positions there. We'll recognize first Dr. Claudio Pellegrini of the University of California, Los Angeles, and SLAC National Laboratory. Dr. Pellegrini, please join Secretary Moniz and Director Holdren at center stage to receive the 2014 Enrico Fermi Award. So this is for pioneering research advancing understanding of relativistic electron beams and free electron lasers, and for transformative discoveries profoundly impacting the successful development of the first hard X-ray free electron laser, heralding a new era for science. So, and so we now recognize Dr. Charles Shank of the Howard Hughes Medical Institute and Lawrence Berkeley National Laboratory. See, these guys do learn from experience. This is for the seminal development of ultrafast lasers and their application in many areas of scientific research, for visionary leadership of national scientific and engineering research communities, and for exemplary service supporting the National Laboratory Complex. So, congratulations. So now we get the pleasure of hearing from the laureates themselves. So we'll start with Dr. Pellegrini.
Well, let me start by thanking the Energy Secretary and Energy Undersecretary Moniz and Franklin Orr and Director of the Office of Science and Technology Policy for their kind words, very kind words, and I want to give again our thanks to President Obama for being so friendly and nice and interested this morning. I am also honored by the presence here at this ceremony of the Ambassador of the Italian Republic to the USA, His Excellency Claudio Bisogniero. I still have an Italian accent. I'm also thankful to all the colleagues, friends, and the family for being here today to share this important event in my life. Receiving the Fermi Award and going to the Oval Office to meet the President is a big honor. And having my name in the group of the people who have received this award before. You mentioned some. It's more than I ever expected in my life. I still wonder how this came to pass. And for this, I must be very grateful to many people at DOE, SLAC, UCLA, and other colleagues who made this possible. Fermi has always been one of my heroes. Being a physicist, you look at Fermi, he's up there in the top rank of scientists of all time. But we have a few things in common. We were both born in Rome. We studied at the same university, and we both moved to the US to pursue our love of physics. Now I have another link to Enrico Fermi, and I'll cherish this link. I'll show it to everybody, people that I know and even people that I don't know. In my life, I have had the privilege of fulfilling my dream and doing what I love best to do, doing physics, being a physicist. And as a physicist, I have been able to give my small little contribution to knowledge of the natural world, continuing that process that started about 4 centuries ago with Galileo and Kepler, and that has profoundly changed our relationship to the world around us, to nature, and to the other human beings. The impact of science is so large on all of us. When did I first dream of being a physicist? This is the fulfilling of my dream. When did I start having that dream? I didn't start in elementary school. That for me was the war years, 1940, 1945, during the Second World War. During those years, my father was a prisoner of war in Egypt, and my mother, my sisters, and I were living in a small village in the mountains east of Rome, and what we were trying to do was to survive and have enough food to eat, enough food to put on the table. After the war, we moved back to Rome, where I started middle school. Middle school was a particular period in my life. To say that my grades in middle school were not good is an understatement. My dream was to become a famous soccer player. Sadly, but probably for the best, by the time I finished 8th grade, I realized that soccer was not in my future, so I better find something else to do. In high school, I became really interested in science. And I must thank for that 2 wonderful teachers, my humanities and philosophy professors. They introduced me to Greek philosophy and to the quest for understanding natural phenomena through reason and observation. I read the beautiful Lucretius poem, De Rerum Natura, on the nature of things, which explained atomic theory, Brownian motion, evolution, and many other things with beautiful verses. I believe that to this day, this is the best book for explaining why science is important. It's important to scientists and non-scientists alike. It explains the beauty, the pleasure of understanding how nature works, avoiding superstition, living with peace of mind, and pursuing happiness. The pursuing happiness is important because 18th century, after Lucretius, the founding fathers introduced the same concept in the American Declaration of Independence when they listed the pursuit of happiness as an unalienable right of human beings. And this is, I believe, a very good reason to love this country. I studied physics at the University of Rome, where some members of the Fermi group from before the war were still teaching, and I read many of Fermi papers. I now have the complete collection of Fermi papers at my home. I am very grateful to Italy, to my birth country, for the opportunity to receive an excellent education, and I still enjoy its benefits and that of an Italian classical culture. At the end of 1958, after university, I started working at the Italian Laboratory for High Energy and Nuclear Physics in Frascati. And something happened in that lab in 1960 when Bruno Tuschek conceived the idea to build an electron-positron collider. So what he wanted to do was to store not only matter, but antimatter. That was a very daring idea at that time. But Bruno Tuschek built a small prototype and proved that it could be done. And so in 1961, he proposed to build a larger collider, Hadone, and he asked me to be part of the team to do that, and I accepted that. That has been an important decision. It really changed my scientific life. Hadone was a great opportunity for a young scientist, and in particular because it brought up a new class of phenomena, the collective instability of particle beams, or we could call them the self-organizational properties of electron beams, which at the beginning limited the operation of Hadone, but there is interesting physics to be done there, and a group of people, including Tuschek, Matt Sens, Ralph Littauer, Andy Sessler, and I, were to understand and control these phenomena, and in the end, Hadone worked pretty well. That gave me an opportunity to meet all these American friends, and in 1969, Sessler invited me to Berkeley for a year-long visit to California. My daughter was born there. They offered me a job at that time, but we decided to go back to Italy. But the US and California remained in our hearts. And so in 1978, we came back again, this time to Brookhaven. And by now, we have been living in this country for the past 37 years. And I must say that we are very grateful to this country for its generosity and the opportunities it has given us all. The Department of Energy Accelerator Physics Office has supported my research during most of these years. And the program officer, and some of them are here today, often provided very useful feedback and comments. And I wish to thank DOE and the officers of this program for their contribution to my work. When I was at Brookhaven, I started to work on free electron laser, including the development of the SASE theory. I'm using a technical term. And I did the initial application of this theory to short wavelengths free electron laser with a young postdoc, Jim Murphy. And at the same time, in 1985, Bob Palmer and I established the Center for Accelerator Physics at Brookhaven, which is still going strong today with Ilan Ben-Zvi and other people. And there we did the initial development of the photoinjector, which is critical for the operation and success of X-ray free electron laser. And that was done building on concepts and ideas of Richard Sheffield and co-workers at Los Alamos. In 1989, we moved again. We like to move. And we went to UCLA, where Joe Radnick and Clarence Hall, who were the Dean of Physical Sciences at that time, gave me the support I needed to set up a new lab and hire a new assistant professor in this area of research. I offered the position to a brilliant young scientist, James Rosenzweig. We started working together on FEL and high brightness beams. We continue to do that. I also had to say that if you are in a university, you have a lab, most of the work is done by graduate students. We all know that. They really did most of the work to establish the feasibility of a SASE-FEL, so to support the theoretical work which we did. Some of these students are here today, and again, I want to say thank you, guys. I want to take a moment to make one point. Most of the initial research on free electron laser was supported by defense funding and was mostly oriented to high average power FEL for defense application. The funding grew very quickly in the 1980s and equally quickly disappeared. My own work was not related to defense. I really was interested in the X-ray region, in really reaching the X-ray region, which we couldn't do with any other system, I believed. And I must also say that most members of the scientific community at that time considered the idea of an X-ray FEL an extravagant idea. But I could do my research, continue my work, because of the freedom I enjoyed at UCLA, in a university, the students that did most of the work, and they're cheap, we know, and funding from the DOE university program in accelerator physics. And I really believe that it's most important for the future of science in general, particle accelerator physics in particular, in the US and elsewhere, to maintain a well-funded university program, open to new ideas and risky proposals, the crazy ideas. In 1992, I came up again with this crazy idea, and I proposed the SLAC to build an X-ray FEL using an existing accelerator. And I was lucky to find people willing to share the vision of this X-ray FEL and accept the challenge. And among them, I want to mention Herman Wienig, Max Gornakia, Andy Sessler, Artie Bienenstock, Bert Richter, and other people that were very supportive. And when we demonstrated in two small experiments at UCLA and Los Alamos the validity of the satellite FEL theory, that this approach would really work, at least at longer wavelengths, the Basic Energy Science Office also had the courage and the foresight to make a risk investment. At that time, it was really a risk investment, and provide initial funding for the project, leading in time to LCLS, the first 1 angstrom few femtosecond X-ray free electron laser. From the idea and the small-scale experiment that we did at UCLA to LCLS, which is really a wonderful, exciting research instrument, there is much work to be done in accelerator physics area, engineering, beamlines, optics, detectors. And the X-ray community and I were very lucky to have people like John Galaida, Paul Emma, Dave Dowell, Effin Glasking, Heinz-Dieter Nuhn, Joe Storr, Uwe Bergman, and others, too many to name them all, in several labs, SLAC, Argonne, Livermore, and UCLA, and Brookhaven, to accomplish this task brilliantly with outstanding results, the outstanding results that we see today at SLAC coming from LCLS. So in the end, I'm here today because I've been heard during my life by many people, colleagues, friends, teachers, and by my family. My father and mother worked very hard to support my education. My sisters encouraged me and helped me all the way. In our 54-year-long marriage, my wife, Maria Grazia, and I lived and worked in many countries, including Italy, Denmark, Switzerland, Brazil, the UK, East Coast, West Coast. And wherever we were, Maria Grazia was always able to create a warm and supportive family environment for me and our children. And our children had worked very hard in all these different places to make new friends and go to new schools. Now the family has been growing with the addition of 2 daughters-in-law and 1 son-in-law and 5 beautiful grandchildren. So I'm really grateful for all of this, and I don't have enough words to tell them all my love and gratitude. But I want to say one last thing to my grandchildren, the youngest members of this audience. Follow your dreams, whether they involve soccer or science or anything else, and pursue happiness. Thank you all.
Well, thank you for those wonderful remarks. So now I'd like to ask Dr. Shank to please take the podium to tell us something of his story.
First, I'd like to join Claudio in our thanks to all of you here on the stage, and in particular to all of the people who did the hard work to propose me for this award. Having been on the other side of this and preparing many other cases for this reward, I know just how difficult and how long and how hard this needed to be done. I'd also like to credit my scientific career the wonderful colleagues who I've had an opportunity to interact with, my students and my postdocs, who all contribute very heavily to the body of work that I have been very fortunate to have been involved in. I thought I'd take the moment today and talk a little bit about my work. Since my talk is going to be about very short bits of time, I will be appropriately brief. I'd like to begin with a quote from a former boss of mine at Bell Laboratories, Arno Penzias, who received the Nobel Prize for discovering the Big Bang. He said, "You know, Chuck, you really haven't accomplished anything significant unless you can explain it to a cocktail waitress at 2 a.m. in the morning." I know where Arno spent his time, but I feel I have a much smaller hill to climb since there are so many smart people in this audience. Time is an important parameter in just about every aspect and field of science. And very short intervals of time, a millionth of a billionth of a second, really have been the focus of my work. And I'm glad the word femtosecond was used here because that accurately describes this time scale. So the question is, what can happen on this time scale? And the answer is, not very much. But what does happen is absolutely amazing and has fueled my imagination for the last 4 decades. I like to call it the world of ultrafast events, a world in which I've let my mind seep into. It's been a place of escape from the helter-skelter of the real world that one confronts when leading a complex enterprise. And it's been something of a really important piece of my life. So I'll try to answer the question the president asked me. So what is an ultrafast event? It's something that happens so quickly that you need a fast shutter or a pulse of light to be able to capture the motion of the event. I'd like to give you a feel for this by drawing upon a historical event. In 1872, Leland Stanford, former governor of California and also the founder of Stanford University, offered Edward Muybridge $25,000 to settle a bet. Stanford's contention was that when a horse trotted or galloped, all 4 feet came off the ground. People didn't believe it. It took Muybridge until 1878 to complete this work. It's not that it took him 6 years, but he had a small problem with a legal event which had to do with the murder of the lover of his wife, and he needed Stanford's lawyers to make him a free man, and apparently that did work. He completed the task with a camera of the speed of 1/2000th of a second and proved conclusively that horses, all 4 hoofs, come off the ground when they gallop. In the world of ultrafast events, we have a shutter that's the equivalent of a millionth of a billionth of a second. Clearly, we're not going to be looking at trotting horses, but rather things that happen on a molecular or atomic size scale. Such things as ultrafast chemical reactions, flow of energy in solids, things of that sort. So the question is, how did we create the tools to do this work? When I began work in this area, it was really at the dawn of the laser age. We had single frequency lasers, but not lasers that would produce many colors at once. If you're going to make a short pulse, you have to have a lot of colors to make the pulse. We discovered a laser based upon organic dyes, similar to food coloring, that could operate in such a way that it could sustain oscillation or operation an entire rainbow of colors across the visible spectrum. And we were able to produce optical pulses as short as a few femtoseconds. This was more than 40 years ago. These pulses were a perfect tool for measurement. By the way, when I talk about this with my kids, they're more impressed with the entry into the Guinness Book of World Records than any paper that I've ever written. We studied a vast array of chemical reactions and processes and solids and liquids and molecules. And I'll try to give you a sense of our adventure with a few examples. At one point, shortly after we reported these pulses, and they were kind of a curiosity, and what would be the real impact of being able to look at things on a very, very short time scale? I read an article by a noted biologist. He claimed that while femtosecond optical pulses might be important for chemistry and physics, there was absolutely nothing of interest in biology. My question, could it be that no one ever looked? And so I set out to prove that wrong, but more importantly, something that I was very interested in, and that is vision. In the eye is a protein called rhodopsin, and rhodopsin had been studied, many chemical reactions, there are hundreds of them, that take place when light strikes your eye and ultimately an impulse goes to your brain to create an image. And I wanted to know, what's the first thing that happens? What's the very first chemical reaction? We knew a great deal about these cascaded events, and it was like searching for the source of the Nile. We knew there was a river there, but where did it all come from? And we wanted to understand this in a way in which we could actually relate it to the physiology and understanding of vision. Well, it's rather difficult to work with rhodopsin, and you don't begin your first experiment with that because you can only use a molecule once and it's gone. So you have a very difficult synthesis to create a small amount of material. So we began with a molecule, a halobacteria, specifically bacteria rhodopsin. It grows in very saline solutions on the bodies of rotting dead herring. It's actually interesting in itself. If you ever fly into San Francisco, you can see colored water pools where they're creating salt ponds to harvest salt. The bacteria rhodopsin is really a good indicator of the health of that salt pond. And this molecule acts and it's called bacteria rhodopsin because the structure is very similar. And it's not identical, but we found that the first reaction for this interesting creature, it uses sun as part of its energy source. And the way it's one of the few creatures that live with sun that are not plants. So it's a very, very interesting little creature. We did, in fact, measure its very early chemistry and its dynamics. And we then had developed our techniques so that we can now do the next step. We had extracted rhodopsin from a cow's eye, had a small amount of it, but we were able to perform the experiment and show that this reaction that takes place, which is really, we have a molecule that looks like two wings of my hand here that are in a twisted form, and when they're excited with light, they lower their energy and the first reaction takes place. We were able to definitively show, to measure that and say that's complete in less than 100 femtoseconds, and it was clearly something that was important for biology and something that did occur in the femtosecond time scale. We went on to do a lot of other things. We actually made a movie very similar to the movie that Muybridge made, but only with time resolution in femtoseconds, where we would take a light beam excited on a crystal, very intense one. The energy would transfer from the electrons we excited to the crystal, and then the crystal would come apart. It would turn first to a metal, and then it would actually blow off the surface. And we were actually able to see all of those elements of that in a movie that we made. Well, in 1989, I joined the Lawrence Berkeley National Laboratory. I was very excited about the construction of the advanced light source, which was well underway, and wondered, would it be possible to make that light source a real source of femtosecond X-ray pulses? Some years later, we made the first femtosecond X-ray measurements with the synchrotron. We were able to actually make a measurement and look at heating of materials and energy distribution materials. Today, that work has been supplanted by the enormous success of machines excited by Claudio Pellegrini here, and the free-electron laser at SLAC is really at the pinnacle of now what's possible in X-rays. In summary, I'd like to say I've really had the privilege of being able to pursue problems that excited my passion while leading one of the nation's most exciting national laboratories, the Lawrence Berkeley National Lab. Thank you all very much.
Well, there's inspiration for all of those in those words. Thank you both for your remarks. Thank you all for your attention, and congratulations to the 2014 Enrico Fermi Award recipients. I invite all of you here to a reception which will take place in the cafeteria, and as you go out the door, there will be a troop of folks going up the escalators to get you there. I understand that the important folks here will stay for just a moment for some additional pictures, and then we will join you. So thank you all for coming.